Course agenda. Next, let's take a look at the course agenda. 1. Logic Design Fundamentals. In this chapter, we will cover basic logic gates, full adder example, simplifying logic functions with Boolean algebra, simplifying logic functions using Carnot maps, designing with NAND and NOR gates, hazards in combinational circuits, types of flip-flops, Mealy sequential circuit design, design of a Moore sequential circuit, state equivalence and optimization in sequential circuits, key timing considerations in sequential circuits, tri-state buffers and their role in digital circuits. 2. Introduction to Verilog. In this chapter, we will cover key concepts in digital design, hardware description languages, HDLs, levels of abstraction in HDL design, benefits of using HDL, roles in HDL-based digital system design, challenges in adopting HDL, key features of Verilog language, basics of Verilog module declaration, Verilog module hierarchy and instantiation. Port connection syntax in Verilog, connecting ports in module instances, using procedural constructs in Verilog, synchronizing module behaviors, naming, rules, case sensitivity, and commenting in Verilog, simulating HDL designs, compilation, libraries, and elaboration. 3. Logic synthesis with Verilog. In this chapter, we will cover understanding logic synthesis, benefits of logic synthesis, using synthesis tools, key steps in synthesis, netlist simulation methods, literal logic inference in synthesis, impact of coding style on synthesis, synthesis challenges and limitations, technology-specific optimization, FPGA-specific synthesis challenges, synthesizable Verilog constructs, Verilog coding style. 4. Designing RTL logic for synthesis. In this chapter, we will cover modeling combinational logic, incomplete event list, complete event list, incomplete assignments, complete assignments, continuous assignments, modeling combinational logic summary, modeling sequential logic, normal behavior, reset behavior, incomplete assignments, blocking versus non-blocking assignments, temporary versus persistent variables, modeling sequential logic summary, modeling latch logic, modeling three-state logic, using synthesis attributes, pragma, full underscore case in synthesis, pragma parallel underscore case in synthesis, pragma implementation in synthesis, pragma sync underscore set underscore set or async underscore set underscore set in synthesis, synthesis attributes, unsupported and ignored Verilog constructs. 5. FSM design for synthesis. In this chapter, we will cover finite state machine, FSM, overview, defining FSM states, read-write synchronizer FSM, 1-block FSM coding, 2-block FSM coding, 3-block FSM coding, 3-block FSM, combinational outputs, optimizing register count, optimizing power and noise, gray encoding, optimizing performance, one-hot encoding, state-bit indexing in one-hot encoding. 6. Preventing RTL and netlist mismatches. In this chapter, we will cover preventing indeterminate behavior, careful use of synthesis attributes, careful use of conditional compilation, ensure complete sensitivity list, handling temporary variables properly, align RTL and synthesis models, handling unknown X values, case X versus cases in synthesis, variable declaration in synthesis, delay controls in synthesis. 7. Managing the RTL coding process. In this chapter, we will cover project naming conventions, partitioning for synthesis, register block outputs, group combinational logic, keep resources together, separate auxiliary and core logic, separate blocks needing different synthesis techniques, partitioning for design reuse, coding RTL for synthesis. 8. managing the logic synthesis process. In this chapter, we will cover goals of logic synthesis process overview, logic synthesis inputs and outputs, logic synthesis basic flow, reading HDL source, elaboration process, applying constraints, map to generic cells and optimize, pruning unloaded logic, optimizing arithmetic expressions, sharing common subexpressions, balance resource sharing and duplication, apply carry save adder, CSA, transformations, chipware library and synthesis, trade-offs, manual macro cell, instantiation, map to technology cells and optimize, technology-dependent optimization, boundary optimizations, register retiming, scan insertion, analyze results, timing report, write netlist. 9. Building Verilog design for synthesis. In this chapter, we will cover FIFO design specification, FIFO implementation, FIFO module components, defining FIFO parameters, FIFO port configuration, FIFO internal variables, FIFO functional behavior, FIFO output status, FIFO test bench overview, structure of test bench module, test bench declarations, instantiating FIFO in test bench stimulus.